Hi everyone, I'm Stephanie Peart, and welcome to the Salty Science Podcast. So in this week's episode, we're getting into one of my favorite topics, salinity. Salinity is really cool, and my research heavily relies on this knowledge, so hopefully by the end of this episode, you'll be running to the top of a hill and yelling out, "I love salinity!" Okay, well maybe not, but maybe you'll at least be able to appreciate it a little more. And before we begin, as a quick reminder to my listeners and new listeners, Salty Science is designed to be a casual, laid-back discussion of marine science topics rather than an intense classroom-style lecture so that everyone can enjoy it without feeling like you have to go back to school. And if you are in school, this is prime study material, just saying. And so each episode is designed to build off of the previous episode. And in these early episodes, I'm more focused on laying a foundation of knowledge so that you can really have fun listening to future episodes when we start discussing more complex subjects like the global ocean conveyor belt, or the biological carbon pump, or upwelling and biogeochemical cycles, and coral reefs, and other topics that have a huge impact on our planet and all life on Earth, including our own. And yes, even if you live in the middle of a desert, this stuff impacts you too. Okay, so in the last episode, we looked at a basic scientific definition of salt. And we also compared the salts found in the ocean to regular table salt. And we also discussed how much salt is in the ocean, if you remember, is 5.5 trillion tons, as well as how it got there. And then we also discussed how salt can change some of the physical properties of water. And FYI, the link to the really cool DIY experiment where you can light a light bulb is posted on the Salty Science Patreon page, so go check it out. And finally, we discussed some of the reasons why salt in the ocean is so important, especially to marine scientists. And then I ended the episode with giving you the challenge to answer the question, why should I care? Or why should someone who's not a scientist care about the salt in the ocean? And I just want to say a quick thank you to everyone who has already emailed me their answers. They've been really good so far. For instance, Tony91820 said, if 50% of our oxygen comes from the ocean, it's kind of important for us all to know something about the ocean. And salt impacts everything, from changing the flavor in foods, and even we sweat salt. And salt used to be used as money, and that's how we got the word salary. So thank you, Tony91820. And actually, from all the responses, I've been inspired to start a special segment once a quarter of having an episode where we just read out listeners' answers to the different answers from the Why Should We Care challenge, because they're really good and definitely eye-opening for me. And I'll pause to say, as a marine scientist, sometimes I feel like I know the answer as to why someone who's not a scientist should care, but getting these submissions are just reminders to me that, oh wow, there's other perspectives out there, and it's really great. Thank you so much for your submissions. And just as a reminder, I'll be having this challenge at the end of every episode. Even if you didn't want to answer the last one, maybe you'll be inspired to answer this episode's challenge. But anyway, moving on. Okay, so in the last episode, we talked about ions. And as a quick reminder, ions are the atoms or molecules with a net electrical charge due to the loss or gain of one or more electrons. And that means that they can either have a positive or a negative charge. And I didn't say this in the last episode, but you'll often hear scientists refer to the positive ions as cations and the negative ions as anions. And if you're a cat lover, this will be easy for you to remember, because if you love cats, you have positive feelings towards cats. Therefore, the positive charge is a cation. And unfortunately, I don't have a good one for the anion, other than maybe there's two N's for negative. Listeners, if you have a good way of remembering anion is the negative ion, please share. Okay, so like I was saying, you have a positive and a negative, and just like magnets, opposites attract and they want to stick together. And when they do, they form a solid crystal structure that we call salt. And of course, if you place salt in water, the salt will dissolve or disassemble because water molecules also have a slight charge to them. Actually, water molecules are what we call polar, meaning that one side has a positive charge and the other end has a negative charge, and they're able to surround the ions and keep them separated. Actually, now that I think about it, water molecules are kind of like parents. When you were a teenager, was there ever someone that you were really attracted to and the quote-unquote chemistry was just there, and you wanted to be with that person all the time, but your parents just absolutely refused to let you see that person? Yeah, water is kind of like that. It keeps ions apart. That is one of the reasons why we call water the universal solvent. And just to throw in another quick term that you might have heard scientists mention before is the word solute. And solutes are just substances that are dissolved in water, so you might also hear scientists referring to these dissolved ions as solutes. Okay, and also in the last episode, we went over the 7 major and 5 minor ions found in seawater. Those being sodium, chloride, sulfate, magnesium, calcium, potassium, bicarbonate, bromide, borate, strontium, fluoride, and silicate. And we call these the major and minor ions because they're found globally in all seawater in the same proportion or ratio. And I mentioned that in science we call this the constancy of the composition of seawater. And of course, there are other ions in the water, but these are the main players. And because we have so many different ions in seawater, they can form different combinations, and so seawater is also a mixture of salts. And the main salts are sodium chloride, calcium carbonate, gypsum, magnesium chloride, and potassium. And after reviewing my notes, in the last episode, I forgot to mention anhydride, which is another salt that can form. Okay. So I did this quick review of the ions and the salts in the ocean because this brings us to our topic this week, which is salinity. So what is salinity? A quick definition of salinity would be saltiness. That is, how salty is the water. And in science, we refer to the salinity as the concentration of salt in a volume of water. And you're probably more aware of this concept than you think. If you were making spaghetti for dinner one night, the first step in cooking the noodles is to bring a pot of water to a nice rolling boil, at least per the instructions of every box of pasta I've ever bought. And I was always told to add a little bit of salt to the water, which after the last episode now makes sense to me because the salt changes the water's heat capacity, making the water heat up faster. But in cooking, I have full control on how much salt I put in the pot. I can either add just a little bit of salt, or I can add a lot of salt, which I don't think I would want to with cooking at least. But the idea is that I have a set volume or amount of water in my pot, and I can either add a little or a lot of salt, therefore changing the concentration of salt. Or, in other words, I can change the salinity of the water. And while I'm saying it's the salt concentration, really it's the concentration of the solutes or ions present in the water. Okay, so this leads me to my next question. How do we measure salinity? And that's actually a question that's been asked for literally thousands of years. Throughout history, as early as the 6th century BC or BCE, philosophers and scientists have asked, why is the ocean salty? What are the components that make it salty? And how do we quantify it? And one of the earliest quantitative descriptions of the amount of salt in seawater was actually by one of the great philosophers of the 1st century AD, Pliny the Elder, who tried to quantify the amount of salt in water with his description, a sextarius of salt and 4 sextari of water give the strength and properties of the saltiest sea. I just find that so fascinating that someone so long ago was trying to do what we literally try to do still today in marine science. Okay, so moving forward. So one of the earliest methods that people have used to try to quantify the amount of salt in the water is through evaporation and or distillation. And this is exactly as you can imagine it. It's where you take a known volume of seawater, say a liter or a kilogram, and let it completely evaporate until quote-unquote dryness, and then weigh the remaining salts. And FYI, this is called gravimetric determination. And this type of method was used for centuries. However, this method, as scientists since the 1600s discovered, is unreliable for several reasons. And one quick example would be that, depending on where you collect the water, instead of just having the salt left behind, you might also have some microscopic plants and animals or other organic matter left behind too, which would impact the weight of the salt that you're measuring. Plus, there are so many different chemical reactions going on in the evaporation process that you might actually lose some of the ions, so that would also interfere with your measurement. And finally, this method is also just so tedious and takes a lot of time. So right around the turn of the 17th century, scientists began trying to develop other methods for quantifying salinity. But the big breakthrough finally came with the HMS Challenger and her research crews around the world from 1872 to 1876. And on this cruise, the HMS Challenger traveled all around the world, and scientists and crew brought back 77 water samples from various depths in nearly all of the major oceans and seas. And actually, the breakthrough came about 10 years later when William Dittmar was able to reliably confirm that all the major and minor ions were made in the same proportion all around the world. And remember, we call this the constancy of composition of seawater. And this is where marine scientists were able to take advantage of this consistency or constancy of composition because other scientists were already developing successful methods to determine the amount of, say, the chloride ion using something called titration. And titration is basically just slowly adding a known concentration of a solution called a titrant to a known volume of another solution with an unknown concentration until the reaction reaches what we call quote-unquote neutralization, and this is indicated by a super cool color change. And a really famous titration method that has been applied to marine science was developed and published in 1856 by Carl Friedrich Mohr. And this method I've actually used in a marine chemistry lab at Stockton University, which the method is kind of fun to watch. You start out with a clear liquid, which is your seawater sample diluted with some DI or distilled water, and you add a little bit of potassium chromate solution, which stains it yellow, and it's kind of like just adding food coloring to your water. And then you slowly add silver nitrate, another clear liquid, 1 drop at a time. And the silver ion drops its nitrate partner to combine with the chloride ion, forming a precipitate or a solid called silver chloride. And this turns the water from a clear yellow to a milky white. And then you slowly keep adding silver nitrate to the mixture until the water turns brick red. And when it turns brick red, that just means that all of the chloride ions are now used up, and now the silver is finding a new partner, which is typically bromide. But it's just really cool to watch. So you go from 2 clear liquids, you stain 1 yellow, and then all of a sudden these clear liquids turn milky white and then turn brick red. It's just really cool. And so going back to this titration method, if we know the amount of silver nitrate used, we can then calculate the amount of chloride in our seawater, and then with a simple equation we can determine the salinity because of the constancy of composition. However, this method, while informative, it leaves a lot of room for error and can also be very tedious. But then in the 1930s, it was finally established that the electrical conductivity of seawater is proportional to its salinity. So remember how I said in the last episode that pure water is a poor conductor of electricity, but when you start adding salt, it enables the water to carry an electrical current? Well, now here we're finally able to take advantage of this information. And so while this was established in the 1930s, scientists still were using the titration method until about the mid-1960s, when we started to make the switch to measuring conductivity. And this is mostly because scientists and engineers were developing better and easier to use sensors. And so since the mid-1960s, salinity has been measured in terms of the conductivity ratio, which is you measure the conductivity of your seawater sample and then you divide it by the conductivity of a standard potassium chloride sample. And then through a rather complicated looking equation, you can measure the salinity of the water. However, over the years, different companies have been able to develop better and better equipment and sensors that now all I have to do is place the sensor in the water, and on the handheld it does all of the calculations behind the scenes for me, and it gives me a really precise reading of salinity that then I can use for my research. And because the reading is actually a ratio, this is why we drop the units and just say a number. Like the average ocean salinity is 35. But you'll also hear salinity read as 35 practical salinity units or practical salinity scale. But it's still really cool to think that regardless of your preferred units, the numbers are still relatable to grams per kilogram or grams of salt per kilogram of water. And oceanographers are still working on better and better ways to measure salinity as well as how to define it. So the rule of thumb is, regardless of what unit you use, 1, always define your terms, and 2, just simply explain why you're using whichever units you want to use. Okay, and before I move on, there is another fast and fun way of measuring salinity, which is actually the first way I learned how to take salinity measurements, and I still use this method when I need just a quick reading to give me a rough approximation, and that is using the refractometer. So salt also changes the way light refracts through water. So you take this little handheld device that looks like a mini telescope or one of those kaleidoscope contraptions, and you place a drop of water on one end and close the lid, and then you look through the other end and you can actually read the salinity measurement. And don't worry, my friends, I'm going to be posting pictures of all of these instruments on the Salty Science Patreon page. Okay, so moving on now. Like I mentioned before, since the voyage of the HMS Challenger, scientists started discovering that, for the most part, all ocean water, all around the world, has roughly the same salinity. And even though there are some variations here and there, if you average the surface waters, the average salinity of the world ocean is 35. However, like I just said, there are variations in the salinity of seawater and differences between salinity at the surface versus salinity deeper in the water column. And even the ancients, like Aristotle in the 3rd century BCE and Pliny the Elder in the 1st century AD, noticed and recorded that there are variations in the saltiness of water with depth. And I'll say it briefly here because we'll get more in depth on this in future episodes. The major control of salinity in the ocean is the balance between evaporation and precipitation at the ocean surface, which we define the surface to be about 1,000 meters or 3,280 feet deep. Because below this depth, the salinity roughly remains constant at about 34.5 to 35 worldwide. Okay, so now imagine for a moment you're looking at the Earth from space, or you're looking at a globe, and look right at the equator. So there's a lot of rain or precipitation at the equator, which this, as you can imagine, dilutes the amount of salt in the water at the surface. So here, at the equator, precipitation exceeds or is greater than evaporation. So you'll have fresher water on top and saltier water on the bottom. Now, if you travel a little further north or south to the tropical and subtropical latitudes, these regions have a high level of evaporation, and when water evaporates, it leaves the salt behind. And so, of course, it would make sense why these regions have slightly saltier water on top than on the bottom. And an interesting side note, these latitudes also correspond to where we have the most deserts on land. And as you move closer towards the temperate regions and the poles, you'll find we have a lot more rain again. So precipitation is, once again, greater than evaporation. And while evaporation and precipitation are two major controls in sea surface salinity, it also depends on how close you are to a coastline with a river mouth shooting out fresh water or areas of melting or freezing ice, because these also play a role in salinity. Okay, and now, just for fun, here are a few quick terms and definitions that we in marine science often use to describe different areas with different salinities. Don't worry, you don't have to memorize these. Okay, so the first term you've probably heard before, brackish. And brackish is just it's a generic general term that we use to describe any water that has a salinity less than 25. And then another term that you're probably really familiar with is brine. And a brine is another general term, which is defined as anything above a salinity of 35. And then getting a little fancier, we have metahaline, which references water with salinity ranging from 45 to 65. And then euhaline, which are waters with salinity between 30 and 35. And then you have polyhaline, which are waters with salinities ranging from 18 to 30. And then mesohaline, which are waters with salinity between 5 and 18. And then oligohaline, which references water with a salinity between 0.5 to 0.5. Okay, so now as we close, why do marine scientists care about salinity? Well, salinity is one of those great foundations that all marine scientists, regardless of their discipline, that is to say whether they're marine biologists, geologists, physicists, chemists, you name it. If someone is studying marine science, all of our research is impacted by the salinity of the water we're working with. And a lot of our instruments and sensors that we use require us to know the salinity. For example, in my research, I measure dissolved oxygen in many of my samples, And I have to know the salinity of the water because I have to tell my sensor what the salinity is so that I get a correct reading, because salinity can impact how much oxygen is able to be dissolved in the water. But more on that later. Okay, so now before I say goodbye, I want to leave you, my listeners, with a challenge to answer the question, why should I care? Or why should someone who is not a marine scientist care about the salinity of the water? If you would like to share your answers with me, you can email me at saltysciencepodcast@gmail.com, and once a quarter I'll have a special episode where we go over some of your answers, which I've already checked my calendar. The first listener answers episode will be the week of November 1st. So you can submit any episode answers before then if you would like them to be read out loud on air. But I can see where this might get confusing for me, so please, if you email me your answers, just put in the subject line the episode number that you're referencing. Cheers. So that's all for now. Until next week, don't forget to take chances, make mistakes. Oh wait, that's Miss Frizzle. Until next week, don't forget to stay salty. Thank you for listening to Salty Science. But guess what? You don't have to let the fun end here. Go to the Salty Science Patreon page, where I've posted some really cool videos, some study notes, as well as some really neat experiments that you can try at home. And if you want to follow along with my own research, you can follow me on Instagram. My username is TEPSAdventure. That's TEPS Adventure. All Salty Science episodes are available on iTunes, Spotify, Google Play, and YouTube, plus another of other podcasting apps. If you like the show, please rate, review, and subscribe on iTunes, as this is the best way to spread the word about this podcast. Salty Science is listener supported, so if you would like to show your support, visit our Patreon page at patreon.com/saltyscience, where you can either make a one-time donation of any amount, or you can become a Salty Science crew member for as little as $1 a month. So visit the Salty Science Patreon page and sign up today.